Time for another Optica online industry meeting, this time on quantum sensing and atomic clocks. This is no longer a niche discussion, it's becoming a strategic race. As governments and industry pour serious money into defence, resilient navigation, secure communications and critical infrastructure, the pressure is now mounting. We need to build sensing and timing systems that can keep working when conventional systems fail. Photonics is not a peripheral, it's central. Take these examples. At Leidos, quantum sensing is being developed to address one of the most urgent defense vulnerabilities of our time, GPS jamming. Their work on magnetic navigation uses quantum magnetometers based on nitrogen-vacancy diamonds. These detect variations in the Earth's magnetic field, creating a path towards navigation without depending on a signal that could be jammed or denied. At RobQuant, we see a different but equally important sign of where the market is going: chip-scale, room temperature quantum magnetometers, built with NV diamond technology and integrated photonics. The goal is to make these systems smaller, tougher and manufacturable at scale. And these are just two examples. Behind them sits a much broader industrial push involving packaging, lasers, integrated photonics and cost reduction. With additional contributions from Quark, Optica, NASA JPL, CSEM, Femtoprint, Ligantech, OE Waves, Coasense, Mania Photonics, Nexus Photonics and Monarch Quantum, this discussion will look at where the technology is moving fastest, what still blocks adoption, and where the first serious business opportunities are emerging. Let's begin.
Hello everyone and welcome to the online industry meeting on quantum sensing. Finally, the time has arrived. We are all here, we are all ready to have an important discussion, a very important discussion. As we say in the introduction, today we depend on very critical photonics and quantum technologies to solve challenges that our governments and our R&D lines worldwide have. And today we have put together one of the most exciting lineups in the quantum sensing industry that you can actually imagine. I'm really excited for what's going to happen on the next 90 minutes. Before I give the floor to John Pugh, I would like to say, first of all, thank you very much to the companies who made the meeting free of charge for everyone. The support, the sponsorship of OE Waves and Ligantech. OE Waves, if you're looking for narrow line width, if you're looking ridiculously low noise, those specifications in low noise that you can actually be very, very worried they are true, they are true. OE Waves provide the lowest noise narrow line width lasers in the market, and Ligantech, the silicon nitride platform that is used by most of the top R&D lines in quantum technologies for integrated quantum photonics. If you're looking for a reliable, stable, low-loss silicon nitride platform, you go to Switzerland and you get it from Ligantech. And I would like to say that today we have a fantastic lineup. This is the rules of the game. We have a group of integrators, companies who are here with challenges, with demands, and they are here to find partnerships. Those are RobQuant, CSEM, Quark, Optica Photonics, NASA Jet Propulsion Labs, and Leidos. For the first time, our new corporate member Leidos in the room. And we have enablers, companies who are here with a solution that the integrators can use to get a unique selling point in the market. And those today are Ligantech, Femtoprint, Nexus Photonics, Menir Photonics, Sense, MKS Instruments, Monarch Quantum, for the first time at an online industry meeting, and OE Waves. Thank you very much, all these companies who are here to find reasons to work together. I would like to also say that we do this for our corporate members. We work for our corporate members. If you like what we do and you want to support us, the best thing you can do is to join as a corporate member and benefit to all the things that we provide: investment, contact with potential customers, market reports, anything that you want. We try our best to help you with. I also would like to say that all of us are meeting very soon in Glasgow on the 16th and 17th of June I hope to see you there. It's going to be a fantastic, spectacular face-to-face meeting. It's co-located with Optica Quantum 2.0. We have a shared exhibition. If you're looking for a place to showcase your technology, you should do it there as well. 16, 17 of June. I hope to see you. I will see you in Glasgow. And also for those of you who are in advanced manufacturing, doing wafer level testing, wafer level packaging, wafer level manufacturing, we are meeting in June at the Global Advanced Manufacturing Alliance Gamma meeting in Brussels. I hope to see you there as well. With this, I would like to remind everyone that the meeting is being recorded and live streamed in YouTube. So allow me to say hello to the YouTubers in the world. Hello, YouTubers. If you have any question, write in the chat and I will read it in the room. And this, of course, also valid for the people here with me in the Zoom channel. If you have any questions or comments during the meeting, please write something in the chat and we'll make sure that you get to voice your own question and to make that meaningful connection. And now it is the time for me, the most exciting time for me is when I give the floor to Dr. John Pugh, Director of Peak and Quantum Technologies at Optica, who is the person who put together that fantastic lineup you just saw. John, what's going to happen over the next 90 minutes?
Well, thank you so much, Jose, and welcome everyone. So I'm delighted to be co-moderating today's very exciting session. So I'm particularly looking forward to understanding how system level challenges like packaging, stability, and power are being addressed as these technologies move toward practical deployment. So as Jose said, this is a very interactive meeting, so please post your questions in the chat and we'll welcome you to unmute and ask your questions directly. So let's get straight into it with our first speaker. Agneta Syme-Olsen, co-founder and chief technologist at RobQuant, focusing on next-generation quantum sensing approaches using nitrogen-vacancy centers in diamond and a unique photonic enhancement architecture. Agneta, please share your slides. The floor and the attention of everyone in the room is yours. Thank you.
Hi everyone, I'm Dr. Agneta Syme-Olsen. I am the managing director as well of RobQuant. So I want you to imagine a world where a patient wears a lightweight hat in their own bed, collecting continuous functional brain data overnight. So today that vision is impossible because high-performance brain sensing is trapped by big, bulky machines in specialized facilities. If you need MEG, so measuring the magnetic fields of neurons firing, you're forced into a compromise. The clinical gold standard at the moment, the squids, rely on liquid helium cooling, and they cost upwards of £2 million and are entirely immobile. And the newer, more wearable challenges, the OPMs, they remove the cryogenics, but they rely on heated vapor cells that saturate instantly in the Earth's magnetic field. So that means the patient is still trapped inside a bespoke, expensive, magnetically shielded room. And it's not just healthcare, so the same sensing bottleneck affects other areas, for example, remote or high-G environments. So these would be too big to send off anywhere, but also they would fail under vibration or magnetic noise. So what we need is a quantum grade sensitivity, but without the infrastructure burden. RobQuant provides freedom from that bulky machinery. We're building a solid state quantum sensor using the nitrogen vacancy or NV center in diamond, integrated directly with standard silicon photonics. Because of our patent pending architecture and on-chip vector field cancellation, our chip is designed to operate at room temperature. It requires no external shielding and it's solid state, so it'll be rugged enough for a jet or safe enough to be on a patient's head. Because our core technology is a semiconductor chip, our business model is B2B. We don't want to become the sort of new medical headset manufacturer. We want to be the core sensing engine. As you can see from our partnership model, we take a component first approach. We want to supply a validated sensor chip, the data sets, and the integration notes, and then our partners can take that component and build the final product around it. We're currently undertaking an Innovate UK grant project to transition from TRL3 to TRL4. That should happen later this month or next month, I mean. The physics is validated, our architecture is defined, and the patent has been filed. So Our company and founding team have just been selected into the cohort 4 of the Chip Start UK program, and we're actively transitioning from grant-funded lab science into scalable hardware business. In addition to me, there's our chief scientist, Joe Smith. He has over a decade of hands-on experience with the sort of NV diamond integration challenges that we face. And we also have Sam Smith. He's a UK and EU patent attorney, ensuring that our intellectual property is taken care of. As a component first company, our path to market is entirely collaborative. We're a team of scientists, so we obviously love the physics, but ultimately we want to work with partners who in turn wants to turn these quantum sensing tools into real world products. As I mentioned, we're transitioning from TRL3 to TRL4, and we're currently fabricating our first integrated devices. So we don't have a finalized chip at the moment ready to ship out, but I think it's still important to open up these conversations now. And what we're really looking for today are people that we can collaborate with. Looking at what we can offer, our first goal is early access components evaluation at TRL4, and leading into collaborative validation studies and eventually the co-development of reference designs. And in terms of what we're looking for research labs, we're looking for partners generating high quality ground truth data to help us benchmark and test our chips. For foundries, to ensure that all of this actually scales, we're looking for packaging and foundry partners to help us bridge the gap from TRL4 prototypes to volume manufacturing. And for system integrators, medical device manufacturers, and so on, we want to understand your real world system constraints, so your size, power, thermal limits. We want to collaborate on well-defined use cases, whether that's exploring consciousness monitoring in a high G environment or looking at continuous brain activity of an esports athlete or something completely different. If you have a clear application, we want to talk to you. So I'm very much looking forward to hearing from all of the other companies today and to discuss further. Thank you very much.
Great. Agneta, thanks so much for joining us. And this technology has great promise, especially to avoid the heat generated by the atomic vapor cells when operating so close to the body and the skull. And a question comes to mind for me is in your architecture, how do you actually position the NV centers so that they're on top of the waveguides, as it were?
This is when I should have our chief technologist, as chief scientist Joe here, because he would be much better placed to answer these sort of questions. That is the sort of research that he's been working on for 10 years. So if anyone wants to know any more, I invite people to ask us
Okay.
any questions offline.
Sure, and I guess the real benefit of PIC integration is the miniaturization and scalability. So when produced in volume, they tend to have very favorable cost implications. So have you identified key applications other than the neurological sensing where that small size is crucial?
I mean, I know there are other people also doing NV sensors in all sorts of but we are focusing at the moment on looking at brain activity. We know that getting to anything like a brain scanner sort of thing is going to take absolutely ages and require a lot of regulatory approval. So anything where we can look at consciousness and that sort of thing would be interesting for us as well.
Great. Well, thanks, Agneta. So I'm going to go to that last ask of yours in terms of foundry partners. So we have in the room Steen Kuyvers from Leidos. Steen, are you able to help Agneta with your low loss silicon nitride platforms? Please share your slide, and the attention of everyone is yours.
Perfect. So hi everyone. So for those of you who are not familiar with Leidos, we are a manufacturing partner and process design house for photonic integrated circuits. So today we are a team of about 80 photonic enthusiasts, and we have offices in Switzerland, where we have our headquarters, as well as in Belgium and France, where we do most of our PIC manufacturing with our volume partner XFAB. So we provide low-loss photonic integrated circuit solutions, which we complement with heterogeneously integrated active devices, which can be used for modulation, detection, and generation of light on the chip. So what can we do for the quantum sensing and optical clock community? Well, first of all, we offer a number of established low-loss silicon nitride PIC platforms. To give you an example, we have, for example, our AN350 platform, which uses a 350 nanometer thick silicon nitride waveguide layer, which we commonly use for realizing ultra low loss linear optical components on a chip. So on this platform, we achieve typical propagation losses on the order of 0.2 dB per meter for a wide waveguide in the C-band, as well as 4 dB per meter for a strict single mode waveguide in the C-band, to give you an example. So this is very well suited for linear photonic applications, but we also have platforms where we use thicker silicon nitride layers, which are often used for example, frequency comb generation and spectral broadening, which are very relevant when building optical clock systems. And to give one example there, we have a project, we had a project with Ghent University and IMEC and some other partners, which is called CSOC, where we implemented both the microresonator-based comb generation and mode lock lasers on this silicon nitride platform to realize optical clocks in a compact footprint. Now, these low-loss silicon nitride-based platforms are complemented with active components. So we are, just to give you some examples, we are also integrating lithium niobate modulators on our platform, which we can use for low-loss electro-optic modulation, as well as indium gallium arsenide photodetectors, which we can integrate on the same chip using microtransfer printing. So this brings together all the optical and electro-optical functionalities on a single PIC solution. So if you're interested in learning more, I invite you to get in touch with us, but I'm also happy to take any questions you have right now.
Thank you so much, Steen. But going to come back to you in a minute because we have a question in the chat for Agneta from Shikata-san from Sumitomo Electric. Shikata-san, would you like to unmute and ask your question?
So thank you very much for the presentation. And I'd like to ask, what kind of diamond material are you employing? Let's say HPHT or CVD or natural ratio or 12C enriched or that kind of thing.
Well, I can answer. I don't have that at the top of my head. I'm sorry.
Okay, we'll connect you following the meeting and we can answer the question that way. But thanks, Agneta. So there's a question for Ligentech from Judith Olson in the chat. Judith, would you like to unmute and ask your question?
Yeah, sure. Often I hear about optical isolation as being a barrier to using PICs for especially like quantum sensing type applications that require narrow line width, very controllable lasers. I was curious if Ligentech still sees this as a barrier to PIC development and integration, or how they have overcome it.
Thanks for your question. It depends a bit. So we sometimes realize optical isolation through nonlinear effects based on ring resonators. There are a few solutions that you can exploit, but sometimes that's a blocking point because they're usually quite narrow band. If you need a broadband isolator, there's generally no other way than to integrate magneto-optical materials on the PIC, and that's also something that could potentially be used or be integrated using microtransfer printing, which is a technique that we are using today for our photodetectors. So if that is needed, there might be a solution there, but that is not something that we have available yet today.
And Steen, one of the known issues with pumping NV centers in stoichiometric silicon nitride is the creation of the excess background fluorescence in the waveguide, and this has a negative effect on the signal to noise ratio. Is this something you've encountered, and does your ultra low loss recipe allow for using it in this way?
Yes, so I would say there is some room to tailor the properties of the silicon nitride base platform to adapt to those specific circumstances without suffering from an increase in loss. So there are some parameters there where we can play with for that purpose.
Great, thank you, Steen. So next, we have a Swiss-based partnership showing how this ecosystem is already working together. So Sylvain Carlin from CSEM and Cesare Alfieri from Femtoprint will discuss system integration and packaging for quantum sensing. So Cesare first, and then Sylvain. The floor and the attention of everyone is yours. Please share your slides.
Thank you very much, John. I'm sharing the slides. Here we go. So thanks again for inviting us to this very interesting online meeting. We are Femtoprint. We're a Swiss-based company with more than 40 people working to create glass micro devices with a micrometric precision and resolution. So we are a contract and developing manufacturer. We work for our customers to realize, starting from glass substrates, 3D shapes with, as I said, 1 micrometer of resolution, and working with substrates that can go up to 30 millimeters in thickness and up to 300 millimeters in diameter. So we are active in many different domains, from micromechanics to micro-optics to microfluidics, but today we want to talk about quantum and not about ion traps. That is one of our most demanded quantum device, but about quantum sensing, and in particular glass devices for magnetometry, vapor cells, and how we can connect them to the outer world with electrical connectivity and optical and photonic connectivity. So I want to highlight a couple of main applications we have. So the first one is the production of integrated microwave antennas for high performance NV probes. So in these devices, we can really take benefit from our production technology, because we can produce these antennas monolithically and realize complex 3D geometries, combining micrometric and millimetric features with this 1 micron tolerance. So I have a couple of examples of how we did this. So the first is an academic example that we developed together with the University of Basel. And so we could integrate this device into a scanning structure that is simple and reproducible and easy of use. But not just that. So a similar concept was also adopted by one of our industrial customers to realize quantum scanning tips that are sensitive also to cryogenic temperatures. And this setup turned out to be easy, especially concerning tip exchange. So this was a way to demonstrate the industrial application of scanning and magnetometry. But we can also realize vapor cells at a wafer level, again, taking benefit from the 3D shaping of glass. This can be done either in standard fused silica, but also with borosilicate glasses, having a very wide freedom in cell geometry. We can also weld glass with glass to create hermetic sealing. Normally, we do this at ambient pressure. This comes from our historical market of microfluidics. And today, we are also developing this capability in vacuum together with the CSEM. Once you have your glass micro devices, could be helpful or could be indispensable to connect them with the rest of the world. So you can do it electrically, and to do that, you can metallize your structures. We can do that. We can deposit metal thin films with sputtering or E-beam evaporation at different angles, producing through glass vias or through also the use of hard masks that we produce and align. We can realize pads and sort of glass PCBs. We can also laser ablate the thin films to insulate some regions. But even more interesting is the optical packaging we can offer. And this is at the base of the collaboration we have with CSCM. So we have expertise in producing glass ferrules, so very precise holes for fiber insertion. We can write directly in the glass waveguides for light propagation. And we can realize optical surfaces in a free-form way. This with a high shape accuracy and high surface quality. All of this then can be combined with laser welding into a complex packaging that can be very useful for applications in quantum sensing. And I would leave the word now to Sylvain for the rest of this interesting story.
So I'm Sylvain Carlen. I'm the leader of the Quantum Tech Group at CSCM in Switzerland. And what I want to show you in the couple of next minutes is how we can use femtoprint technology to improve the miniature hot vapor quantum sensors and the atomic clocks that we're developing at CSCM. A couple of words about CSCM. So we are a non-profit research and technology organization. And we're active in the field of electronics and microtechnology. And our goal is to transfer the technologies from the academic world to the industrial sectors. And that's typically what we do with the quantum sensors that we develop for our clients for real-world applications. Our developments in the field of miniature quantum sensors are based on a common platform, which is composed of three key building blocks that you see here. The first one is the MEMS atomic vapor cells, which is really the heart of the sensors we develop because they contain the atoms. Then we have the miniature physics package platform, which brings together all the required physical elements to probe the atomic vapor cell. And finally, we have an electronic, integrated electronic, which allows to operate the full system. We apply this platform for a large variety of application, which ranges from atomic clock to magnetometers, gyroscopes, frequency references, and radiometers based on Rydberg atoms. Our MEMS atomic vapor cells are fabricated using conventional cleanroom techniques. They're composed of a stack of silicon glass, which is assembled by analytic bonding at a wafer level. And we have a quite large choice of customization in terms of filling with alkali metal or buffer gas, vacuum, and in terms also of surface functionalization on the inside or the outside of the cell, depending on the requirement and on the application. Now, in terms of physics package, you have here an example of different realization that we've made. On the left, you can see the details of our concept for miniature atomic clocks, where you can recognize the different elements needed to operate the clock, the MEMS atomic vapor cell, of course, but also an isostatic holder for thermal management, micro-optics planar waveguide to route the lights in the system, and DIL 14 cover for vacuum encapsulation. And that's the typical state of the art of what we're doing currently at CSCM. But we can also reach a higher level of integration if we try to go beyond that with the femtoprint technology. And that's what I want to show you here. That's what we're doing in the frame of a NISA project, where we develop a new physics package platform together with femtoprint. With their technology, we can produce an all-glass monolithic sensor. So we get rid of all the discrete elements, and we can directly include all the optical connection, electrical connection, freeform optics as well to route the light inside of the package. And eventually, we will also be able to directly encapsulate the full sensor with the glass. So altogether, that will allow to create a very compact and robust sensor And in the frame of the project, we will demonstrate that first on a laser stabilization module. But of course, this technology can afterwards be directly applied to all the different types of sensors that we're developing. With that, I'm done with my presentation. But if you have any questions, please feel free to ask.
Great. Thank you so much, Cesare and Sylvain. So these are very impressive developments. Are they being driven more by a technology push or by concrete requirements from end users asking you, like from space and defense technologies?
Probably it started, on our side at least, it started with a technology push, and now it's shifting towards a requirement from either aeronautics or space industry, and also a bit from biotechnologies, I'd say.
Great. And if the demand suddenly increased tenfold, 100-fold for the systems, what part of the system would break first? Is it the materials, the packaging, the supply chain?
Good question. I don't know, Cesare, up to which extent your process is scalable.
Yeah, I don't think we'll be the ones breaking first. So we have capacity and we can scale up for these kind of devices. At the moment, I would say we are under capacity. So there is still a lot of development and a lot of research, and so few quantities, low number of pieces, high added value, but we are very ready to scale up whenever it's needed. And to be honest, the antennas I have shown are already a good example. So we're not producing few of them, but we already saw a ramp up.
Cesare, that was going to be my question to you. You mentioned, complex 3D geometries, and my question would have been, are you able to go to volume production with those? And the answer is, of course, yes. So yeah, going back to you, Sylvain, how much of your roadmap depends on advances in lasers and photonic integration in that sense? Can you comment further on the laser unit you showed for the miniature atomic clocks? And
yeah, one key element for at least for the atomic clock, maybe it's a bit different if we target a magnetometer, but for atomic clocks, one of the key elements is the VCSEL that you have inside of the cell, inside of the package. And actually, the availability of this VCSEL is a key point for industrialization, because today there aren't a lot of people providing such lasers at the desired wavelength. It's a bit of a niche market today. The wavelength is 795. We can also work at 780, but for rubidium, what we use at CSCM is 795.
Great. So there was a question in the chat from Min Tran of Nexus Photonics on what wavelength do you need, which is a great way to segue into Min's slide from Nexus Photonics. So Min, are you able to help in this front?
Absolutely. More than happy to talk about Nexus Photonic technology and how we could help the industry moving forward with this. So, hi everyone, this is Ming Tran, VP of Research at Nexus Photonics. We are a company based in Santa Barbara, and we've been building the beyond silicon performance lasers and photonic chip that manufacturing with silicon infrastructure. So our mission is to combine the performance of advanced photonic material like lasers and other material for optical functionality with the scalability and manufacturability of silicon photonics. And as you can see here, our platform enable on-chip light sources across a broad wavelength range from visible all the way to IR. As you can see, a few wavelength that being tested under wafer scale, at 460 nanometer, 780, 940, and 1550. So we support the full flow of photonic chip development, including design, fabrication, testing, back-end process, packaging, and to deliver the application-specific pick for customer. Depending on the application and partner, we can provide a full solution or just selected part of that flow. Our goal is to enable high-performance photonic that is compact, high-performance, scalable, cost-effective, and of course reliable for customer. Let's zoom in a little bit on one of the most critical building blocks in quantum sensing and atomic clock, the lasers. So at Nexus, we're developing widely tunable lasers. You can see the spectra across the range. Some of the 90 tunable lasers that we demonstrate in the past, and we are growing the lasers portfolio, wavelength portfolio constantly. Our lasers has very low noise. As you can see here, compared to VCSEL, our standard tunable lasers have more than 100,000 times lower noise. Typically, the lasers can be widely tunable and operating in a kilohertz Lorentzian language range. And if customer want to push that even further, we offer a solution with self-injection lock to push it down to hertz level. Another cool things about being able to put lasers compactly with other component on the same chip is that you can have all the functionality to allow cell calibration with on-chip wavemeter, with photodiode and all that, with very compact footprint and manufacturable with low cost at high scale manufacturing. Beyond the laser itself, we are also build application specific picks with a growing component library that includes lasers, amplifier, photodiode, and optical I/O, all kind of beam shaping that you would need for your operation. So we believe that the futures is integrated photonic system that are more robust, more manufacturable, and more deployable at scale to replace today's bulky optics and assembling lasers that really limiting your cost and the size of the system. And thank you very much.
Thank you
Happy
so
to
much,
take
Min.
question.
Yeah, thank you so much. And you're integrating these lasers directly on chip across this wide wavelength range from visible to telecom. So what are the key performance trade-offs? Are there any? You've mentioned a lot of benefits, but are there any trade-offs compared to discrete laser sources?
Apparently, there's a trade-off in terms of what we can do on the chip. So how to get such a low noise lasers it all depends on the quality factor of the resonator, and we have seen constant improvement over the year with, for example, silicon nitride, low loss, and high Q resonator. But the bulk optics still today is still better. So I mean, with time, we're gonna be able to compete more with the bulk optics. But currently we are still below. But what we gain with integration is we can put a lot more component and functionality on the chip.
Great. Steen Kuyvers from Leidos, what's on your mind?
Yeah, I was just wondering if you have any trouble with the thermal management of the lasers on your picks, or how you handle that.
That's a great question. Thermal and laser, they don't like each other. So we have to do a lot of engineering design to mitigate that. But one thing that work in our benefit is that actually compared to telecom wavelength, a lot shorter wavelength, for example, 940 or 780, they are performing much better in terms of thermal because of the band gap being larger, and you have more favorable quantum well structure there.
Right, thank
Okay,
you.
So thanks. We have a question from Matthew Aldis from AQuark in the chat. Matthew, do you want to unmute and ask your question?
Hi, thanks, John. Yeah, question for you, Min. If your performance is beyond what a conventional silicon platform can offer, what material platform do you use? Is it silicon nitride or something else?
You're talking about the waveguide below the 3.5, or I mean I can let me give you a general answer then. So the way we integrate and make this laser end pick is that we use heterogeneous integration. We start with the base waveguide, which can be silicon nitride most of the time, that because it's CMOS compatible and all that. But we also use lithium niobate as waveguide and to give us the very high performance modulator as well. And then we bond 3.5 chiplet on top of that, and we make latest modulator, latest amplifier photodiode, and also modulator on the 3.5. So that's how we address all of the wavelength, different wavelength and functionality. Does that answer the question, I guess?
It does, thank you.
Thank you very
Great.
much.
Well, thank you, Min. That's a great way to segue us into Matthew's talk. So, we've seen how you integrate laser functionality onto chip. The next step is what enables that at system level. So how do you take those capabilities to actually reduce size, weight, and power in real quantum systems? Matthew, please share your slides once Min has stopped sharing his. And
there we go.
From Santa Barbara to the UK, the floor and the attention of everyone is yours.
Lovely. Hi, everybody. Thanks for the invitation to speak with you today. I am a representative of AQuark Technologies. My job is timing lead, and that means that I'm responsible for looking after all of the applications for the quantum technologies that we develop and exploit for timing applications. The company's grown reasonably quickly over recent years, starting as a spin-out from the University of Southampton in the south of the UK. It's grown through several stages of support from different funding bodies and is now approximately 23 people strong, with a second-generation atomic clock prototype ready to go out to some of our potential customers for field testing. Cold matter is at the heart of what we do, and it's at the heart of the quantum technologies that we're hoping to enable to be shown and demonstrated as tools for good in the world around us. We focus on three main sensing areas at the moment, one of which is electric fields, one of which is gravity, and the main first available product that we're aiming to get to the market is the clock, which is, of course, sensing time. We're also interested in things that could be done with magnetic fields, acceleration and rotation sensors in the fullness of time. But for now, the focus is on these top three items. We're trying to operate in a trade space of cutting through and applying timing technology to new areas where it might not have been possible historically by introducing new rugged engineering and high performance cold atom systems. We're looking to cut through in terms of cost and particularly size, weight and power requirements while achieving a compelling performance for customers. The system is based on something called the super molasses trap, which was a discovery of a novel technique for trapping cold atoms without the quadrupole magnetic field that's usually required for neutral atoms. That's going to be combined with advanced semiconductor wafer bonding techniques and eventually integrated into microliter scale vacuum chambers with bespoke vacuum management techniques that we include in there. The super molasses trap's name comes from beyond molasses. It involves low microkelvin subdoppler temperatures, and we've measured millions of atoms appearing in this trap with very, very low optical power input. So this is some significant advantages in terms of miniaturization. If you don't need your quadrupole field coils and you can get away with much lower power lasers, that opens up a lot more options than most people have available to them. Another neat feature of the geometry is that you are able to create multiple traps in the same chamber should you wish to create an array simply by increasing the number of optical beams with the right spacing. But we hear a lot of the time that cold matter systems require bulky vacuum and don't travel well. Well, we've tried to put that to the test by demonstrating portable cold atom systems at frequent intervals. It needs multiple lasers, and locking them is very hard. Well, we've heard today from a few people working on interesting challenges to do with miniaturized laser spectroscopy systems, and we're working on our own version of that. The accurate spectroscopic reference is a Doppler-free spectroscopy module, fully fiber coupled, integrated in a matchbox size container, magnetically shielded, with all of the internal electronics for producing an RF error signal output. You do need to do the demodulation outside at the moment, but we're working on a solution for that as well. It has even been tested on a mocked up rocket sled simulation of a launch into space, and it performed very well by our standards. So we're very happy to present this to the community as an option for locking lasers in the future. But it's too complicated to use cold matter at the core of a portable atomic clock. Well, we've done it. So we've already finished development of the first phase. The first generation prototype has developed into a second generation, and we are currently looking for opportunities to trial these outside of the laboratory. We've got a few things lined up already, but if you're interested in talking to us about how we might be able to apply the A-clock to your challenge, please do get in touch. We're looking at something the size of a 3U rack mount in a 19-inch chassis, reasonably low power for a cold atom system, and stability targets that I think will address quite a few end user challenges. We're working on the future applications of this technology as well, with plans to develop a clock suitable for spaceflight. This is at the moment a very early days benchtop lab demonstrator, but it uses some different techniques which we think will enable us to reduce the size, weight and power considerably and aim for CubeSat deployment scale. Thank you to everyone here in the community for listening to my slides today, and thanks also to the broader national community in the UK. We've had a lot of support in terms of trialing, test and evaluation of this system, and we would like to invite anyone who has any challenges or challenging environments they would like to see our clock tested in to please let us know, and we'll see what we can do.
Congratulations, Matt, on the great job that you are doing. And we also would like to congratulate the broader UK community and the broader global community. You were speaking, Aquar was speaking at the first ever Quantum Industry Summit, I remember, in Paris, and I love to see the progress that you have done over the last 3 years. It's very impressive. I hope also to see you in Glasgow in 2 months. I hope to see you there and we can meet and continue developing the progress. Matt, your work with the STL is watched by many investors, by many end users, by many space agencies. How can we help you? Can you share with us a couple of challenges, maybe one challenge that the people in the room can help you with?
Something that's already been mentioned in the chat, and Elizabeth Olsen also mentioned, is the optical isolation is one of the main things that we think about, keeps us awake at night. That and reliable splitting of in the long term, we're looking to put everything on photonic integrated circuits as best we can. But where we do have, in the meantime, fiber splitters with reliable polarization extinction ratio, that's something that's of great interest to us as well. Integration of all the optical sources together onto one unit would be a dream. And laser locking electronics, we're working on a lot of things, detection of unlock events, all sorts of things, Jose, all sorts of things that we could talk to everyone in the room about.
I love laser locking. I love frequency comms. Are you working with frequency comms now? Do you have any particular challenges or needs on that respect?
At the moment, we're not working with frequency combs directly. We have a microwave frequency reference. We have options. We think of investigating what we could do with frequency combs in future.
Let's do that, Matt, because Andrea Pertoldi is here from the fantastic, beautiful, amazing Swiss company Menir Photonics. Thank you very much for being with us. The floor and the attention of everyone is yours. Please convince my friend Matt that we need to use frequency comms.
Hello, hi everybody. Let me just share my slide quickly.
Matt, I pay for the shipping expenses of the Menir laser to go to your lab.
Yeah, you're speaking my language.
Yes, so here just a brief slide on, oh wait, let me just make it big. Yeah, just on how we can help the community atomic clocks and the quantum sensors. As you know, at Mini Photonics, we do low noise, compact, ultra-fast lasers with repetition rate in the tens, hundreds of megahertz up to 10 gigahertz in range. And when locked, these lasers can be used as optical frequency comms to reference and increase the stability of the lasers. So for instance, we can transfer the stabilities from a reference to or the lasers, or also vice versa. We can take the stability of the clock transition and give it back to all the lasers in the systems. At the same time, this frequency comm can also be used as a high resolution spectroscoper and in a dual comm manner. Another way that we can help is by allowing frequency and time transfer, as when the laser pulses come, they come with an extremely precise timing, and this allows to distribute the timing signal with femtosecond level precision. This allows to synchronize the clock and the sensors over long distances, as this timing signal can be transferred with fiber. At the same time, and this is the most exciting part of our company, towards a compactness and ruggedization of our lasers, and we will be able in a few years to produce fully automated frequency comm modules of the size of a matchbox, with compact design, ultra low noise performances, and scalability up to thousands of units per year. So this is where we're heading, and if this kind of laser module would be helpful for you, just let me know and I can provide more details.
The question clear for Matt is obvious, and for me as well, is how do we make this smaller? Which companies can help you with that?
Components, we are using already wafer scale optics that will be picked and placed by a robot to fit into these miniaturized devices. At the same time, the stabilization electronics would be needed to be smaller, but we are already working on it, on providing the electronic feedback to stabilize the lasers.
Matt, as an integrator today in the room with Awkward Technologies, and of course with the partnerships that you're doing with the industry, is there any particular challenge that you would need to have fulfilled before exploring a potential collaboration with Menir Photonics?
I think the miniaturization challenge that we've discussed is probably the top of the list. And I think there's some very interesting, credible things that you've discussed today. So yeah, I think we'll be talking more. Thanks.
Fantastic. And we continue, because one of the things that we wanted to talk today was to have new companies that can help the industry, showing their technology very quickly with one slide. And the next one is a very interesting company. We are talking about a fiber-based solution that is able to measure with very low losses, almost no insertion losses, intensity, wavelength, and intensity, wavelength, and bandwidth. I am really more than happy to have today the company Cohersense. Thank you very much for coming to your first online industry meeting.
Yeah, thanks for having us. I hope you guys see my screen. What we do is what one of our partners described as the multimeter for lasers. And with many technical people, that sets exactly the right tone in people's heads. I'm Oliver Leschenko. I'm the founder and CEO of Cohersense. What we do, Jose mentioned it already, is we do provide the two numbers on a laser that are most critical: power and wavelength, and bandwidth that people like, but then the system gets more complicated. And what we support is the stabilization of people's lasers by monitoring power and wavelength simultaneously in a very compact device about the size of your finger. Index finger. We also provide a couple of status flags, and what we usually do is we have people turn intuitive thought of how they think their laser behaves into real actionable results by closing the feedback loop on that. How's that look? It's a very compact device about the size of 2 boxes of matches with a casing around it to make it useful on the lab. I think a better way to think about it is if you compare it in terms of real estate, it takes up on an optical table or an optical system. And just to give you guys an idea, here it is on an optical breadboard table. You have to look really careful because you might miss it. It's right down here. Relatively new on the market. We launched at Laser in June last year, and our system is customizable. So we have not worked directly with quantum. We focus on tunable lasers in the gigahertz domain, but our technology does scale, and we're looking forward to work with the market. Of course, launching was a big step. The other one was, of course, catching the recognition, and if the biggest name in the market with Hamamatsu is recognizing what you're doing there with the Photonics Innovation Award that we got at Laser, that really feels good. So if we can help anybody stabilize their lasers, let us know, reach out to me afterwards or at info@COAS.de. Looking forward to working with every one of you.
There are actually many of your partners in the room, companies like Blana, like Genoptic, like Monarch Quantum, one of the new ones coming in the industry, coming really strong in the industry, and one very established one. Today, we had the pleasure of welcoming with the role of an integrator, because we wanted to honor what Optica is doing as integrator directly serving the quantum sensing market. We had the honor and pleasure to welcome to the stage our next integrator sharing their challenges with the industry, Axel Friedneuer from Optica Photonics.
So my name is Axel Friedenauer. I am the project manager of the optical clock activities at Optica Photonics in Germany, and I'm going to report about the latest addition to our product portfolio, which is a single ion optical frequency standard based on an single ytterbium-171 ion. And this activity is based on the OptiClock project, which was a funded project by the German government between 2017 and 2020, with the goal of developing a transportable single ion clock based on ytterbium-171. The consortium consisted of 6 companies and 4 academic partners, and this was the starting point of our own optical clock development, which is now called OptiClock, which we pursue in a collaboration with PDB, the German National Metrology Institute. Let's briefly take a look at the schematic overview of the system. We start with on the upper left with a clock laser system, with a clock laser, which is a external cavity diode laser emitting at 871 nanometers, and its output is stabilized to a ULE reference cavity to achieve the required short-term stability. This means time scale smaller than 10 seconds. And a second output is frequency doubled to the blue spectral range and used for spectroscopy of the electric quadrupole transition of a single ytterbium ion to ensure the long-term stability. Now, if we take these 2 building blocks, this is what we refer to as an optical frequency standard. And now, if we take an optical frequency comb and stabilize it to the third output, we transfer the optical stability into the microwave domain, and finally we can down convert the repetition rate of the frequency comb to useful signals such as 100 megahertz, 10 megahertz, or 1 pulse per second, thereby turning it into a full optical clock. So in contrast to all the miniature systems we've seen before, our system is still macroscopic, so it's accommodated in 2 19-inch racks, and I'll briefly walk you through the subsystem in the following. First of all, we have the cooling laser subsystem, which consists of 4 diode lasers integrated into 1 rack drawer to address all the relevant transitions of the ytterbium ion. These are stabilized via high finesse wavelength meter, and then we have custom designed light processing units for applying sidebands, fast switching, splitting, and combining of signals. The second subsystem is the clock laser system, which consists of a reference cavity at 871 nanometers, which is a commercially available system, and a custom designed clock laser system, which accommodates the clock laser itself and provides the frequency shift for stabilizing to the correct cavity mode and stabilization of all fiber links within the system. Finally, we have the physics package and the real-time control electronics. Part of the physics package is the ion trap in its ultra-high vacuum chamber with magnetic compensation coils, fluorescence detection optics, beam projections, and magnetic shielding. all of this is controlled by the Sinara Arctic real-time control electronics. All data is recorded and stored in a time series database and visualized via a Grafana dashboard. After finishing the system, we did a full metrological evaluation of the system at PTB to determine the stability and to evaluate the uncertainty budget. And the stability was determined to be 5 times 10 to the minus 15 over square root of tau, which leads to a 1-day fractional uncertainty of 2 times 10 to the minus 17. The absolute accuracy was determined to roughly about the same values, also 2 times 10 to the minus 17, dominated by the black body radiation. Now I was asked to speak about challenges, and and one challenge is if you look at this upper plot, you see that there are a few blank spaces in between there. So I will report on one challenge towards the 24/7 operation of the system, and one of the reasons for these blank spaces is dark times of the ion, which might last up to several hours. And in this period, there is no steering of the clock laser. Therefore, its output might drift away according to the latest determined cavity drift rate. And what are the reasons for these dark times? So one of the reasons might be that the ion is lost from the trap, but this is rather unlikely since we routinely have storage time of several months of the ion. The ion might also be heated up due to a collision, but there we have automatic recooling routines in place. Then the third option is photochemical reactions, which might happen from time to time, but the intensities used here with the beams are so low that it's also rather unlikely. So the predominant mechanism is insufficient repumping from the F states to which the ion might go to. And since this is a quadrupole transition, one needs really high intensity to repump from there and a very good beam overlap. And that is rather difficult to optimize. But in the end, we managed to do so and now routinely achieve like uptimes between 98 or 99% over several days or even weeks of operation. So that's all from my side. Thanks very much for the opportunity to speak here.
Axel, thank you so much for coming. So once you've solved the dark iron problem, are we at the point where more improvements are needed, or is the bigger challenge now to make these systems smaller, cheaper, and more robust for deploying into harsh conditions?
Right. I mean, one of the key aspects is definitely robustness, because as you've seen, it's a really complex system with a lot of lasers also in the deep UV, and there are really a lot of challenges getting all the lasers stable and everything. So I would say the main focus is robustness, and then second comes swap, of course.
Sure. And in the world of ion trap quantum computing, for example, there's a clear push towards replacing these kinds of multi-laser cooling systems with PIC-based multiple grating coupler beam formers, and you can route them on chip. Do you see that as a realistic path for optical clocks, or does achieving this level of performance still require discrete, very high-end laser systems?
I mean, so right now we're working with Ytterbium, which has transitions in the UV. So I guess there is no PIC material platform which can work with 370 nanometers, which would of course be highly desirable. So maybe we have to move to a different species where the wavelengths are more accessible. But I would be looking forward to having PICs in the system, of course.
Great. Well, thank you so much, Axel. So we've just seen how you bring together an incredibly complex system, multiple lasers, frequency stabilizers, ion trapping to deploy an optical clock. But But at the heart of this is the laser performance itself. So the next question, how far can we push this laser source in terms of power, tunability, and line width? And what does that enable at the system level? So we have Yvette just here from MKS Instruments. Please show us what you can do to help.
Good morning. Thank you for that. Let me share. So, as you mentioned, I'm from MKS Spectrophysics. My name is Yvette Just. I'm a product manager there. And I'm here to talk about our Matisse laser today. It's a very high power, over 7 watts, tunable narrow line width system. We have a TI-SAF version and even a dye laser version. The basic TI-SAF goes from 668 to about 1068, and with attachments for doubling or mixing, you can get to 206 nanometers all the way up to 4,500 nanometers. It's very narrow line width, about 300 nanometers of mode hop-free tuning. We have customers that'll use it for atom trapping and cooling, but also in other areas like Bose-Einstein condensates, atomic clocks, quantum computing, microcavity resonators, and high-resolution spectroscopy. So if you're looking for more power and better detection limits, or need more atoms trapped, or a wavelength that's not covered by other lasers, then the Matisse is something that could be for you. If you're interested, please let us know. We'd be happy to talk with you about that. In addition, slides that I don't have here, MKS covers a wide variety of products. So we can also provide the breadboards, very stable breadboards for these to go on, mounts and optics to get the beam to where you need at your sample. And we even offer microwave sources for growing diamonds. So if you're interested in any of these, I can't really talk to you too much about those, but I can direct you to the right person that can.
Okay, well, thank you so much, Yvette. You're clearly pushing performance in terms of power, stability, and line width. We've seen some very small lasers today. So how do you think about that trade-off between performance and system size or complexity?
It is quite a large laser, especially compared to a lot of the things that we have been looking at today. But it is a lot of power, and miniaturizing something with that much power would come with complications. But we are always trying for more power to get as much as customers need.
Great, thank you so much, Yvette. So before we move on to the next speaker, there's a question in the chat from Josiah Green. Josiah, would you like to ask your question, and who is it targeted at, please?
Yeah, more than happy to ask. Thanks for bringing it up, and really appreciate the conversation today. It's a really simple question. At the end of it, I'm curious to know what your electronics challenges are. With atomic clocks and quantum systems, constantly looking at where people are developing, what's in the industry, and we want to make sure that we're giving customers and researchers, developers the tools that they need to be successful. So that's the foundation for the question, and I know it's a pretty broad, open-ended question, but happy to take any thoughts and such. So yeah, thanks.
I guess, Axel, are you able to take a view on that in terms of your complete top-to-clock system? What are your challenges with electronics in that system?
I mean, most of the electronics used in our system is homemade electronics, and we're also relying on the open source Arctic system, which is very versatile, but it's also not very complex. So, I mean, there are not so many real-time, like flexible real-time electronics platforms on the market. So they are always very specialized, and yeah, maybe that would be a route to go.
Okay, great. Well, thanks, Axel. So we're going to move on now to a great recent collaboration between NASA JPL and Monarch Quantum, where integrated photonics and laser systems are being developed for the first planned space-based quantum gravity sensor. So I'd like to welcome Jason Hyun and Rob Williamson to the room. The floor and the attention of everyone is yours.
Thanks. I'd like to thank Optica for providing an opportunity to seek industry partners in enabling science missions from space. So our key role as a government agency to provide opportunity for industry to participate in enabling future missions using quantum and optical technologies. As you may know, JPL has implemented a couple of quantum sensing capability already in space called Atom Lab from International Space Station, Deep Space Atomic Clock, and Deep Space Optical Clock, optical communication, and then also SEEK, which is a entanglement experiment from International Space Stations. Today, I'd like to focusing on something called the quantum gravity gradiometer. Our partner, Monarch Quantum, will also introduce a key laser optical system as a part of the quantum gravity gradiometer. I'm going to briefly talk about the mission objective of the quantum gravity gradiometer, give you a little more detail of the instrument setup, and then talk about how we acquire these industries to partner on advancing our technology, and then switch over to Monarch to introduce themselves. The quantum gravity gradiometer mission objective, there are three main objectives. One is to demonstrate the quantum gravity gradient measurements using end-to-end system from low Earth orbit, 450 kilometers above the ground. And we're going to be integrating many different optics and quantum technologies as a system, be able to advance the capability of the U.S. industries in the field of quantum sensing and instruments and operations. And then we would like to also inform the decisions to reduce risks for the future science-grade instruments. So as a first technology demonstration, we'll be only testing as a system, but for the science grade, we need to improve the performance of the system by order of about 5. So there's a significant step to go through. Through this technology demonstration, we will be doing end-to-end system testing, hardware and software that's needed to provide the measurement. And then lastly, also engineering quantum quiet spacecraft to host those instruments in the future. There are 4 main components of the system or subsystems of the system. The light blue ones are the JPL activities. The pink one is the atomic physics package, will be provided by Inflection. And the orange one is the laser optical system, which will be provided by Monarch quantum system. We will be demonstrating the full system. As I stated, there are 2 chambers by cooling rubidium atoms to picokelvin temperature, and then we'll be flying over different mass and be able to generate gradients and then translate those measurements for mass change detection. For the science grade instruments, we foresee that it will be based on different atomic source. Right now we're using rubidium, but for the science grade, we anticipate it will be a cesium atom. So we anticipate other partners, other technologies to be incorporated for the future missions. So we're continuously engaging new industry to advance these technologies. For our acquisition strategy, first, our sponsors and partners are NASA Earth Science Technology Office, Goddard Flight Center. Originally, we're working with the German space agencies also, and then also university partners like UT Austin. And the scope, once again, demonstrating instrument design, implementation approach, and then also developing a technology roadmap for the full science grade instrument. We surveyed about 20 different vendors. We found 5 credible responses from those vendors. And then we have finally selected the 3 vendors to SBIR, Small Business Innovation Research Fund, to phase 2 awards. And then after the 9 months milestone studies, we selected Inflection and Monarch Quantum as a key partner to develop this instrument. Our long-term strategy needs 5 order magnitude sensitivity
Thus, we need to continuously advance these technologies. So all other industry partners are welcome to provide us their achievements or their capabilities so that we can consider them for future partners. With that, I'd like to transition over to Monarch to introduce themselves and discuss their capabilities.
Thanks, everyone. Thanks for the opportunity to share today. Thanks, Jason, for that. I'm the VP of Business Development here at Monarch Quantum, and we build what we call quantum light engines. These are ruggedized photonic subsystems, and these enable our customers to scale, building larger systems. It also allows them to deploy systems such as out to space, including the quantum gravity radiometer. So our focus is really taking complex lab-based photonic subsystems and transform these into truly engineered, reliable infrastructure that allows real-world quantum systems to go out into the world and do sensing, for example, in this case. So a little bit about our technology. These quantum light engines, they integrate critical photonic components, such as the stabilized lasers, electro-optic and acousto-optic modulators, and we also put in amplifiers, and these end up go into fiber-coupled modules. These include low-noise electronics, control electronics, and these often integrate with our customer subsystems in a seamless way. And these are purpose-built systems. These are built for quantum computing, networking, as well as sensing, and they're built to our customers' and requirements. By doing this allows us to allow our customers to focus on their quantum systems, to focus on those challenges, such as the cooling, the vacuum chambers, a lot of the aspects that are quantum. And we provide the lasers and the classical systems that enable those to be scaled. This partnership with both Inflection and JPL is really a nice reflection of the approach we take with all of our customers. It's really based in systems engineering and deep partnership. We really sit and listen and work extremely closely with our customers to understand their requirements. Often their requirements are quantum derived. Those requirements are what are needed to make ions, atoms, vacancy centers behave properly and produce value. Our work in working with that partnership is doing the systems engineering that will translate those specifications into classical specifications down to engineering specs that we can build systems that deliver. We align with our customers' roadmaps as well, so we understand where they're headed and align the technologies that we develop and mature so that they line up with what they're doing. A piece of that, very important, is addressing some of the supply chain challenges. We have a history of and work with our vendors to mature their supply chain to make sure that these systems end up being reliable, scalable, and deployable. And as I mentioned before, really working with Inflection and JPL is a pleasure. It really shows that tight type of collaboration. It really, you can't solve these kind of problems without very tight collaboration. The problems are very challenging. Understanding the quantum systems, understanding the applications, and then turning those into systems that really will work when they're deployed. It really requires partnership and trust, and that's we really enjoy what's been going on here and with our other customers.
No, thank you very much. I must say, Rob, I would like to congratulate you and your team for entering the industry with such a boom. It was so amazing to hear so many fantastic experiences and discussions at Photonics West and the events afterwards. Coming from San Diego, you really are making an impact, and we love that. An impact through partnerships, and we love that. And when you came with Jason today by your hand, that was really a great addition. Jason Hyon, thank you very much for presenting that fantastic acquisition strategy study. Could I ask you, what is the biggest challenge that you see, and which companies maybe in the room could help you with that?
Well, I think the challenge is on everything. As you know, our technology demonstration, we're trying to launch 2030, and then our science grade instrument, we foresee that try to launch in 2035 and 2037. So we're looking at 5 to 10 year kind of down the road, but we need to improve the sensitivity by order of 5. So there's a significant technology advancements that we need, so we need to continuously engage in working with the industry. And it's not a step function, it's a gradual advancement. So we need to find an opportunity to work together with the various industries to continuously advance it. So our strategy is, there are many technology development opportunities along the way. So we want to continuously be informed of advances and progresses that the industry makes, and then we like to partner with them to demonstrate those capabilities as we are maturing the whole system.
Jason, we have had several people from JPL coming to many of our events, and very often they are followed up by many requests for introduction. We have a lot of opportunities for collaboration, but I would like to highlight one, of course. Matt from AQuark, after seeing this study and the challenge that Jason has in improving sensitivity by a several order of magnitude, what is the first thing that comes to your mind?
Hi, thanks, Jose. Hi, Jason. Great talk. And also thank you, Rob. That was really interesting to see what Monarch's up to. I would just like to ask whether you think there is an opportunity for AQuark to become involved in this project in future. We have some plans to develop gravity sensors at some point. And I think that we would like to see what the supermolasses trap could bring to this technology.
Yeah, please contact us, not only the gravity gradiometers, but we're also developing Rydberg microwave sensors, optical clocks, magnetometers, you name it. So we're looking for all different partners as we are advancing our science measurement from space.
Thank you.
One thing that I would like to tell everyone is that John always loves to say the best for the last. This is one of our biggest, most recent corporate member. I'm more than happy to welcome to the stage a company that for many years we've been dreaming in having in our events. I see their logo at every airport. I see their logo at many of the key locations in the world for related to energy, security, safety, communication. Ladies and gentlemen, I can't be happier when I welcome to the stage Elizabeth Iwasawa from Leidos.
Oh, thank you for such a generous introduction. No pressure coming up from there. Can you hear me all right?
Loud and clear.
Yeah. Well, we're thrilled to be joining Optica as chip integrated photonics is one of the key drivers of our quantum strategy. So let me pull up my slides very quickly. Awesome. Great. So I see that we're sort of bumping up on time, and I know there's another talk after us, so I will be efficient in my use of time. So I wanted to give everyone a heads up about basically what does quantum technologies look like at Leidos. As you mentioned, we do work from everything from cyber to AI to, I guess, our most prolific and least endearing TSA presence. Very cool developments will be happening in that area as well, but not quantum for now. But we do a huge amount of quantum work integrated with all of our big product line and TRL 9 capabilities. So we're not just doing, individual quantum widgets, we're looking at them within a bigger picture of customers that Leidos has, problem sets that we have. I think it was mentioned in the opening video, some really cool work that we're doing with the Defense Innovation Unit and MIT Lincoln Labs for flying NV centers for magnetic navigation. That's a good demonstration of taking sort of like TRL 9 classical, incredible work in magnetometry and then tying it with cutting edge physics. So we are kind of looking at doing partnerships like that and pushing the edge in quantum research ourselves. We do payload development for space platforms, for maritime and ground domain. We do ruggedization. So we have all of this infrastructure that we've used to make cyber secure platforms and payloads that we want to deploy. And now we're seeing if we can augment those capabilities with quantum. The bottom left-hand corner is my usual pitch for chip-integrated photonics and photonics in general, which I think I do not need to sell this crowd on. You all know why this is such a great way to move forward. And kind of we sit in this interesting middle as a R&D organization within a big systems integrator. We partner with academia to do rapid testing and deployment, rapid testing and foundry process development, theory, simulation, some of that more fundamental cutting edge work. We work with foundry partners across the company. These are three we've contracted with this year, and we're always looking forward to expanding that and seeing what we can take advantage from the really critical work that you are all doing. We work frequently with government and civil customers. So we work on DARPA programs, ARPA idea challenges, and a lot of this is immediately focused on applications. So a little less, how can I make the better, stronger, faster sensor, but more once I make it, how does it actually impact the mission space? How can I use it? Is it too sensitive for what we're doing or the platform we want it to be on? So those are some of our principles. We focus on a few key areas. Photonics. A lot of our work here is kind of using photonics as a bridge to take cutting research from partners or our own groups to shrink them down to deployable footprints. And then looking for tricks to help us increase sensitivity. We've got a lot of interest in fast optical switching. We focus on sensing and communications mainly. You'll notice a lack of computing here. That is not one of our key focus areas. We are really interested in sensors, networks, and using that to derive novel information that you can get on the battlefield, covert secure communications, and really pushing forward what you can do with sensor fusion between distributed quantum and classical sensors, how the network can help that, and then how we can make all of that retrofittable for the infrastructure that we already have, because no one wants to relay fiber optics. We also do a significant amount of work in post-quantum cryptography, driving cryptographic resilience at enterprise scale. Not quantum, not photonics, so we're not going to talk about it here. We have a broad variety of research that we're deriving at the sort of photonic level, from exploring working with other foundries to develop visible wavelength PDKs, working on frequency combs, nonlinear optical thin films, and sort of the interface and integration between rubidium and PICs. I think you've heard a lot of talk about, wonderful research that we can push forward with rubidiums and atom traps, and we're really trying to find out, can we reduce the footprint and do really interesting capabilities when we look at the interface of those two devices. We have a broad variety of interests in the sensing area, from quantum RF sensing or Rydberg sensing, depending on who you talk to, sort of counter bio, rad, and nuke sensing. But our main two focuses are the programs are the DIU quantum magnetometry that we talked about, and then quantum gravimetry, which I'm going to talk to you about here. You'll find frequently in defense, no one ever talks about sensing. It's really hard to discuss sort of military-focused sensors, which is why working with the Department of Transportation is so wonderful, because we can talk about our civil use cases. So there are plenty of things that we do sensing-wise, but this one is a little easier to mention externally. So what we are looking to do is design and build a low-SWaP quantum gravimeter that we can integrate with Leidos' autonomous drone platform capabilities and our experience within LiDAR to sort of revolutionize infrastructure analysis. It's a very, very expensive and time-consuming process to maintain bridges and culverts and all of our critical infrastructure. It's billions of dollars of work. It's laborious, and it's frequently sort of limited to subsurface work. So what we are exploring, and we try to take a sort of non-Kool-Aid approach to quantum, is how will quantum create a great improvement here? And if so, how will it do so? And what are the benefits we can bring by doing sensor fusion between gravimetry and LiDAR? So we just won the phase 1 of this innovation challenge. We're currently proposing to phase 2. And there's a lot of public work on that. And this work is being led by material scientist on my team, Dr. Ben McDowell. So happy to connect you if you want to talk to the PI of this particular work. And then there's that MagNav work we talked about with DIU, where we're working on transitioning quantum sensors. So the previous work was, we're driving the PIC, we're driving the quantum innovation, and then integrating it with our capabilities internally. This now we've got Lincoln Labs and FIE working on creating that the sensor payload, and our job is to really push that magnetic anomaly map and the navigation capabilities. So we're doing the transitioning part. And sorry, I think I said FEI earlier, F. So we have flight tests that we're doing on airborne vehicles, and we're integrating it now and seeing just where the improvements are and where the challenges are. This is really cool work. It's been going on for a couple of years, and I believe they're making sufficient improvements that there are follow-on programs. And then I think I can discuss here, you can see this big sensor payload down on the bottom left. And part of the cool part of this work is not only are we working on revolutionizing the map and how you can navigate with the quantum information added on top of, classical magnetic navigation capabilities, but incredible work being done in reducing that footprint to something that instead of hanging below a platform will actually be integrated with it. So I think I ran over here. I apologize. Thank you very much for your attention. Happy to talk about questions. And yeah, we're very glad to be a part of Optica at this point.
And we are very glad to have you in Optica. You can't imagine how glad we are. It is a huge opportunity for our members to find a system integrator that goes all the way to deployment. This is for us an immense value for our membership. What
I was trying to cover with this is
challenge. Sorry, go ahead, Elizabeth.
I was just saying what I was trying to cover for this, and this is my pitch to everyone listening within Optica is, we need everything from, the quantum team who's looking for a tiny laser partner all the way up to, are you looking for a platform partner? So the breadth of collaboration that's available here is pretty big. Sorry, please go ahead.
If we think about the main challenges from many of the systems, could you select one challenge? You will be very happy if today John or myself make a nice introduction to a company that can help you with.
I mean, I saw your comment about supply chains in the test in the location there. What actually picking one is very hard, but I think one of my pleas would be obviously, if you're working in defense and as a defense-focused system integrator, we have to be very careful about our supply chain. I know my team is dying to work with Tech, but there's a lot of our work that we can't do with sort of foreign-based companies. So if you want to open a US office, we would love to do more work with sort of local-based teams. So part of it is, it's difficult to collaborate internationally, which is so critical when you're developing these capabilities, when you're also trying to take care of national security. So there's that balance. And then anyone who's got a good approach to tiny lasers, you know where to find us.
You have made my friend Stein Tech extremely happy. I can see him smiling. Stein, you are actually, many of your customers are working on DARPA projects. So you have managed to find a way to enter the US defense market. Could you help us on that and tell us that you're going to open a US office maybe?
Well, a US office might follow, but that's currently not available. But indeed, we have been working with quite some US companies, also US defense companies. So there might be workarounds to still collaborate. So I would still invite you to have a quick chat, and we can see if we are able to support.
Yeah, I think right now we're actually working with UMD to send some test devices to you. So we're already trying to sneak in some collaborations with university partners. So.
Elizabeth, you're going to be one of the keynotes at the Quantum Industry Summit. Leidos will also be at the Global Photonics Economic Forum. We are so happy to have you on board. There's going to be many introductions to you. And the next one is very important because whenever you are doing anything on quantum technologies, noise is your biggest enemy. And to have really ridiculously low noise, Ori Johnson is here from Oi Waves. Ori, thank you very much for being our final speaker of the day. Send us with a blast of energy and very low noise. The floor is yours.
All right. Thank you so much. Thank you for an excellent webinar, everybody. Yes, Oi Waves brings the low noise. We've seen some very impressive things on chip here today. And our smallest package that really delivers is the 30 millihertz line width laser. We have packed 2 of them in the size of a tuna can to help people really integrate low noise into their applications. We're whispering gallery mode resonator-based lasers, and of course, since we created these extremely low noise lasers, we had to figure out how to measure them. And out of that came the noise analyzer line, where we can measure phase noise from a single hertz to 40 gigahertz in terms of the offset, and RIN all the way out to 110 gigahertz if needed. Another exciting product we just came out with is the 200 gigahertz tunable range RF source. So you can tune from 250 megahertz to 250 gigahertz, actually. So that is another extremely exciting product. And we are, at the moment, not your premier photonically integrated circuits partner, but that chip size device there down there in the bottom corner, bottom right corner, is 29 photonics components packaged into that. So we're your microphotonics partner when you're developing your systems.
Thank you very much, Ori. I am really impressed. But first of all, every time I see your booth at any exhibition, I just come and say the same thing. Is this specs for real? And the question is very clear. How can you measure 30 millihertz?
So actually, for 30 millihertz, we had to build a few of them and beat them together. That's what we had to do for that. And then we used our RF and noise analyzer to analyze the beat note from that.
Congratulations on what you are achieving. Congratulations on the great traffic that you had in your booth at OFC. I see great things happening to OI Webs, and I see great things happening to entire industry. I would like to allow to thank everyone for the last 99 minutes of their time. It was, in my opinion, a fantastic experience.